Making me download Gradle again. Aggravating. So you can download Gradle as an executable, or you can download it as a zip file. And the zip file doesn't need administrative rights, so it's a lot better. All ready now, guys. You guys ready to start class? Yeah. All right, so I had to go ahead and re-download Gradle. If you do want to download it, just and it's not your computer, you can download the zip file, and then that'll make it so that you can run it without administrative rights. But again, I'm not going to ask you guys to do this yourself, but there will be questions on how to interpret the coefficient estimates and the standard errors, right? So before we get back into this, let's kind of do just a quick stats review in terms of what a t statistic is. So what's going to happen is we're trying to predict something, right? Like we're trying to predict test scores from some beta naught plus beta 1 times the student-teacher ratio plus beta 2 times, English language learners as a percent, and whatever the case may be, right? And these numbers, these betas, these are the money. These are the things that we want. These are the things that we're going to estimate, and these are the things that we're going to be interpreting, right? So essentially, with all these betas, we end up getting two things, right? We end up getting a coefficient estimate. So I believe it was like negative 2.28, right, was the beta 1 that we were given. And so I'm putting a hat on it because anytime we run these regressions or we get these results, they are estimated results, okay? So the hat is a reminder to me that this is estimated. It's not the true beta 1, right? Because there's a true beta 1 in terms of what is the relationship between student-teacher ratio and test scores. I don't know that true beta 1. I'll probably never know the true beta 1. But what I can get is the estimated beta 1 hat. And as long as there are some conditions that are met, I can then infer this is approximately the true beta 1. Okay? Or we want to keep in mind that these are all just estimated values. Why is that important? Because any estimated value has it has a margin of error. And the margin of error for these coefficient estimates is called the standard error. So we're all very used to the notion of a standard deviation, right? Where, you know, say we have some set equal to 1, 2, 3, 4, and 5. The average of that set is going to be that's 5 plus 5 is 15 divided by 5 is 3. Yes. English, so that's the English learning as a percent. So that's one of the variables that we used at the end of last class. So English language learners as a percent of the class. It's just another variable that we're trying to predict the test scores for. Yeah, it's just a particular example. So standard deviation. So we had a set of numbers. So there's 5 numbers. We have an average, right? Anytime we have a bar over something, that means it's the average. And then how do we calculate the standard deviation? Well, we look at the variance first, right? And what's the variance? The variance is the squared difference between each one of these numbers and the average, right? So it's going to be 1 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared. And then sometimes we divide by n, sometimes we don't, but that's not the point. The point is the standard deviation is just the square root of this mess, this 1 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared. So this standard deviation, what is it trying to do? It's trying to crunch down these 5 numbers, right? In terms of how much do they vary from the average of those 5 numbers. So it's saying how much, you know, above or below, what's the absolute value essentially of the typical variation that we have for this set. Does that make sense to everybody? And so now, very similar to standard deviation, we have standard errors. The interpretation is essentially the same. It's how much the coefficient estimate varies, you know, above or below that true value. So, in our example, right, we had a beta 1 hat. Sorry. We have a beta 1 hat of, you know, negative 2.28. And, let's just say the coefficient estimate is, well, let's just do it because I have all this stuff. So we're going to run a regression. So remember, what did we do? We essentially ran an XY scatter plot with test scores on the y-axis, with student-teacher ratio on the x-axis. So we have a linear relationship between the student-teacher ratio and the test scores, right? And it's estimating, it says least squares fit, so that's the only kind of regression that we need to know in this class, least squared regression. So it automatically plots a line using that least squared fit through the points and gives us the slope, right? Essentially the relationship between y and x, when y is test score and x is the student-teacher ratio. Now, what we need to do is we need to run an actual model in order to get the kind of nitty-gritty in terms of, how much do we trust that negative 2.28, right? So we put the test score as the dependent variable, because the test score is the thing that we're predicting, it's that y variable. And then we put the student-teacher ratio as the x variable. Remember, we always click the robust standard errors because our data is never, it's never evenly distributed. And then we click OK. And so remember, we can look at it this way, and we can look at it with the view as equation, right? So we're used to thinking about things as the view as equation, and that's what the graph tells us at the top left corner, right? Is the view as equation part. So essentially, I have a standard error on my coefficient of 0.52. So we're going to round that to 0.52. So this is the, sorry, not the coefficient, this is the standard error. That's the coefficient. Coefficient estimate. So it's the same thing as saying the beta 1 hat, coefficient estimate. And then we've got a standard error of 0.52. So what is this standard error telling us? So there's two main ways that we can interpret it, okay? So the first way is by doing a t-test. So this is where we take the coefficient estimate, we subtract the null hypothesis, and then we divide by the standard error. And so I heard some sighs of happiness when I said null hypothesis, because everybody loves stats. The null hypothesis in all of these is going to be that my beta whatever hat is actually equal to 0. So it ends up being really nice because these all collapse into coefficient estimate over standard error. So you take the coefficient estimate, that negative 2.28, divide it by 0.52, and then essentially you're comparing it to, is it bigger than, you can round up to 2, but the proper number is 1.96. So is that bigger than 1.96? Well, oh, sorry, is the absolute value of it bigger than 1.96? The answer is yes, right? 0.52 goes into 2.28, over 4 times, right? So this t-test gives us a value of, around 4, which is definitely greater than 1.96. So what does that mean? That's a very good question. 1.96 is the critical value when we want to be at least 95% confident. It's given. Yes, I'll give it to you in the prompt. I'll give it to you in the problem. It's the default one though. Like 95% of the, I shouldn't say that. 99% of the time you'll use this one. Okay. Very rarely it'll be 2.58, 99%, and then it might be 1.56 for 90%. But those are the only three critical values that you'll need to know in this class, probably any classes that is quantitative. So this is telling. So what is this saying? This is saying that we're like 5%. So this is saying that we believe that beta 1 hat is less than 0, right? So it's this negative 2.28. It's always going to be less than 0 because the standard error is so small compared to that value. And so we believe that beta 1 is less than 0 and that it's around the negative 2.28 in terms of the incremental effect. So we can reject the null hypothesis, because the null hypothesis was that it actually equals 0, right? And so then the alternative hypothesis is that the beta I hat is not equal to 0. And so we never accept the alternative hypothesis, right? We either reject or fail to reject the null hypothesis. So we either reject or fail to reject the null. You can never accept the alternative hypothesis. The alternative side. So this time we're gonna reject the null hypothesis. Does that make sense? So there might be like a trick multiple choice question on there that asks you guys about accepting an alternate hypothesis or rejecting the null hypothesis. And I just want to stress that you can never accept or reject the alternate hypothesis. You have to always phrase everything in terms of the null hypothesis. And so when you reject the null hypothesis, you're saying, I believe this coefficient estimate is around what it says it is. If you fail to reject the null hypothesis, you can never accept it. But you can fail to reject it, then you're saying it could be 0. I just don't know. The coefficient estimate is so broad, okay? And so the next way to think about doing this, and this is the way that the book, is so insensitively puts as the rule of thumb or whatever, right? But the next way, and so it's using that same number. So this is way number 2. It's getting a confidence interval. So the book says that 95% of the observations will fall between, and it's the coefficient estimate, so the beta hat minus 2 times the standard error, so they use sigma for that. Everybody uses sigma for that. Beta I plus 2 times the standard error for that. This is standard error. And so let's do an example with the beta 1, right? And so it would be negative 2.28 minus 2 times 0.52. And then negative 2.28 plus 2 times 0.52. And so this is going to be negative 3.28, rounding, and this is going to be negative 1.28, right? And so the point of this is, when I'm doing these confidence intervals and things, I'm looking to see, is 0 in my number line? Is 0 in this range? And since it's not, since, you know, this, if 0 is right here, this is negative 1.28, this is negative 3.28, here's 95% of the time where that coefficient's going to be. So it's all to one side of the 0. And so as a result, I'm going to reject the null hypothesis that it is 0. So if 0 is not in my range, then I reject the null hypothesis that the value is equal to 0. So either one of these is going to tell us the same thing: confidence interval and the t ratio. So the other thing, well, we don't need to worry about p-values. Just worry about t-stats and confidence intervals. Don't worry about p-values. I think it's easier. But it's whatever way your brain works. You know, either one of them is fine. You either have to take the coefficient, divide it by the standard error, compare it to 2, or put the confidence interval, you know, calculate the confidence interval and see, is it completely to one side of the number of 0, right? Is it all in the negative zone? Is it all in the positive zone? Then we can reject the null hypothesis that it's equal to 0. And I want to stress that's really all we're doing, is we're just saying it has a positive impact, right? We oftentimes really give these coefficient estimates a lot of like weight, right? But if they're not precisely estimated, then all it's saying is it could be between 1 and 1,000,000. That's still statistically significant and positive, right? But that's a huge range in terms of the impact. So that's another reason why the confidence interval may be better, just in terms of, you know, getting a better intuition for what's going on with data and the relationship, right? Because at the end of the day, what are we trying to figure out? We're trying to figure out, is it worth it to hire more teachers to lower the student-teacher ratio? Is that going to result in higher test scores in the future? That's going to result in higher funding that's going to pay for the expenses of hiring the new teachers, right? Is it economical to hire new teachers and lower the student-teacher ratio in my county in California? That's the whole purpose of this data set, right? So let's go back to the data real quick. So we know from calculating our t ratio and calculating the confidence interval that this negative 2.28 is statistically significant. We can also see that in our regression output, right? By looking, they calculate the t ratio for us, right? They don't do the absolute value of it, so we have to do that ourselves and say, okay, the t ratio is negative 4.39. Absolute value of that, is that greater than 2? Yes, it is. It's statistically significant at the 95% level. That's different than 0, right? The stars are just telling me the same kind of thing. If it has stars, it's statistically significant. 1 star is 90%, 2 stars 95, 3 stars is 99. That's not always going to be the same. You have to read the footnote in whatever chart you're reading, because sometimes 2 stars is 99%, sometimes it's 95. I've even seen it as 90, right? So there's no one convention for these stars, but they'll always say in the bottom, when they talk about the data, they'll always say what the stars mean, okay? But we don't need the stars. The stars are like cheat codes, right? We understand what the t ratio means, and we understand what to compare it to in order to figure out, how do I believe this coefficient estimate? Do I really think that there's around a negative 2.28 impact on the test score for every 1 increase in the student-teacher ratio? And so I would say, yes, I do believe that. So then, like I said last time, it's not as simple as just a straight OLS calculation. You know, we have to include other things in there, like the English, the percent of students that are learning English as a second language. We should also include average income, and let's go ahead and run that regression. And so this is, again, this is a case where the coefficient estimate on student-teacher ratio is no longer statistically significant. Sure, it's still negative, but it's very close to zero. The standard error is 0.3, right? So if I were to calculate that confidence interval for this range, you know, it would be 0.66 to positive 0.54. Right? It'd be negative 0.66 to positive 0.54. So it's going to have zero in that confidence interval, which is why the t ratio is so low and why there's no stars. So we can't really believe this estimate. These other estimates, though, they're looking good in terms of as the percent of English language learners in the county increases by 1, the test score is going to decrease by 0.48. And as the average income increases by 1,000, the test score is going to increase by 1.49. So what's part of the problem with these models? Part of the problem with these models is the fact that everything's entering into it linearly. So what if there's a non-linear relationship that's actually going on between some of this stuff, specifically between, you know, average income, right? So what can we do? We can go ahead and we can add a square of average income. We can add that square of average income to the right place. And that was the exact same thing. Okay, so real quick, let's take a look at a graph of test scores and average income. That doesn't look linear, right? Now let's take a look at test scores and the squared of the income. So it looks like it fits the data a little bit better. We could also do what's called a logarithmic transformation, which is just another way of getting a nonlinear estimate here. So let's go ahead and graph these variables. So that's student teacher ratio, sorry. I wanted to do average. Model. No, not model. View. There you go. So then if we do a logarithmic transformation of them, and what a logarithmic transformation is doing is instead of looking at the raw test scores and the raw average income, it's looking at the change in test scores and the relative change in test scores and the change in average income, right? So it's not necessarily the case that, like, if we look at just the straight, you know, an extra $1,000, you know, down here is going to have a different impact on the test scores than an extra $1,000 up here, right? And so we see that it kind of starts to run away from us over here in terms of a nonlinear relationship. And so that's why we take these logarithmic transformations and essentially rerun it with these transformed variables, and we'll get our last model that we'll talk about. So we rerun this with L of test scores, L of student teacher ratio, L of average income. Keep the English language percent there. And we still end up getting pretty crappy results for student teacher ratio. There's a reason for that. I think part of it's because, let's define a new variable. Let's do an interaction variable. And this is equal to student teacher ratio times English language percent. So I think as your English language percent increases for different student teacher ratios, it's going to have a different impact, right? If you have a small class and there's an increase in the number of students that are learning English as their second language, that's going to impact things differently than if you have a large class, right? And so the way that we factor that in is we multiply them together, make an interaction term, and regress that. Nope. So yeah, so this, I'm not doing a very good job in terms of showing you good regressions that have a lot of statistical significance. But that's okay. That's honestly part of data science and part of analytics is doing a lot of different variations, a lot of different functional forms of this stuff, and trying to figure out what works the best. So let me do one more, just linear test score, student teacher ratio, average income squared. Let's get rid of these dudes. Nope, still not good. Average income showing up really statistically significant, right? Both the linear version of it and the quadratic version. So what is this telling us? What are these two variables telling us about how average income interacts with test scores? Right, and it's increasing at a decreasing rate, right? So the slope of the linear variable is positive and statistically significant. So we believe that it's positive. And then the slope of the quadratic variable, right, is negative. So that's telling us the rate at which it's changing. So it's increasing. The average income has a positive impact on test scores, but that positive impact is eroded as income grows, right? So as you get to higher and higher incomes, an extra $1,000 has less of an impact. That so the $1,000 when the average income is $15,000 is going to have more of an impact than the extra $1,000 when the average income is 55. Yeah, exactly. That's what this is saying. Okay. All done with this. So again, you won't need to know how to calculate this stuff, but you will need to know how to interpret the coefficients and just kind of what a least squared regression is, and that standard rule for how to make the confidence interval with 95% of the data. Any questions on that? Okay. So let's jump in. Oh, that's right. I want to get signed into the connect up here. This is get to the book. So I'm going to do some problems. All right. Awesome. So, number one, who can tell me what kind of production function this is? She's like, I'm going to sleep then. No, don't go to sleep. What kind of production function is this? Oh, it's the end of chapter 5. Page 169. So we've got 3 types of different production functions that we learned about in chapter 5, right? What are they? This is why I also prepared a very heavily edited down PowerPoint, because I was afraid that y'all. So, all right. So the different types of production functions. We have linear. So this is Q equals F of K and L equal to A times K plus B times L. So where A and B are constants. So this is the very simple one that we all learned initially. Come on, focus, me. Killing me slow. All right, then we have Leontief, named after a guy named Leontief. And these are when inputs, this is a weird one. Inputs are used in fixed proportions. So Q equals F of K and L equal to minimum of AK and BL. So this set notation means whichever one of these is cheaper. So, you know, they can just use capital or they can just use labor. Oh, sorry, no, they have to use both in fixed proportions. So A and B are constants. And B is a constant. I know that the Leontief functions, they look like L's. K and L in terms of the production decisions. Oh, and so it's essentially saying you're going to produce right here always, minimum. That's what this is saying. Because there would be no reason to employ more capital, right? If you were at that point like this, it would be inefficient. Because you need things in fixed proportion, right? You would have too much capital for the labor that's provided. And so you would decrease your capital and go down to this point. Because each one of these, this is, you know, producing 100 units. This is producing 200 units. This is producing 300 units. Questions? Because you need exactly the same amount of K and L, right? So you would need 3K and 3L in order to make 100 units. So why would you employ 6K to still just make 100 units? Right. Yeah, because whichever one, like one of them is gonna bottleneck you. It's gonna hold you back. And then the last type of production function, which is our most common type that we have, is the Cobb-Douglas, named for two guys. And this is assuming some degree of substitutability. So we've got Q equals F of K and L equal to K to the A power, L to the B power. These are multiplied by each other, where A and B are constants. Yes, that's a times. What? So the question was this one, yes. Units do not have to be proportional in this instance because there's substitutability between it. So I want you guys on your own to calculate the marginal products for the linear. So what's the marginal products for the linear? Marginal product of capital and marginal product of labor. And then I want you to do it for the Cobb-Douglas as well. The marginal product of capital and the marginal product of labor. All right, go ahead and take the next 2 minutes to do that. What? Then we'll do questions. Oh, I just want you to use algebra. Correct. The answer will be in terms of those. That's an L, yes, correct. That's an L, that's K, that's an L, that's K. All right, Savannah, what do you think? What's the marginal product of capital for the linear one? You can phone a friend. Uh-huh. So no, it's okay, it's okay. So it's not that's like the average product of labor or whatever. You know what I mean? Like that's kind of close. It's still wrong, but it's kind of close to that. Okay, so what's going on here? So we want to know the margin. We want to know how much does one extra unit of capital get us in terms of production, right? So if I was using 3 units of capital and 2 units of labor, right? And if this was, let's say this is 4 and this is 5, okay? So then it ends up being 4 times 3 plus 2 times 5. Oh yeah, sorry. So 4 times 3 plus 2 times 5, right? Because I'm just doing B times the L, and I'm doing A times the K, right? And so that ends up giving me some amount, right? 12 plus 22. And then what happens if I increase and go to 4 units of capital and 3 units of labor? Then I'm going to have 4 times 4 plus 2 times 5. So it ends up being 26, right? And so the difference between these two is going to be 4, right? That's 4. It adds 4 to it. And so when I go from 3 to 4, my total production increases by 4. Why does it increase by 4? Because that's what my A is. So the answer is A. Yes, just the algebra, absolutely. So yeah, and the MPL is B. Very good. Yeah. So here, so we have Q equals F of K and L equal to A times K plus B times L. And then what we end up doing is we're taking a partial derivative of this with respect to K. And so when you take a partial derivative, and so these should be partials, my bad. When you take a partial derivative, if the K isn't a part of the term, you just get rid of it. You don't care about it anymore. So since we're taking the derivative with respect to K, the only thing we care about is this A times K. And since it's A times K to the 1, when we use our regular power rule on this, right, it ends up being A times 1 times K to the 1 minus 1, which is A times 1 times K to the 0, K to the 0, anything to the 0 is 1. So it ends up just being A times 1, which is just A. So I think that, I think a big thing with what's going on here is that we're having trouble. So the way that this course is designed and the way the book tests and everything like that, like you can just memorize this. It's not a requirement for you to understand the calculus behind it, but I think it's going to be more difficult for you guys to try and memorize it than to understand a little bit of what's going on with the calculus, because it's just going to be this power rule stuff. So you can just memorize the fact that with a linear production equation, the marginal product of the capital is the coefficient on that variable, right? Whatever is times that variable, and the marginal product of labor is going to be B, right? And so we'll go through the algebra real quick of why that is, the calculus and algebra. But again, you're not going to be tested on it. I just think it makes more sense. But this could just be me because I have a math brain, right? So Q equals F of K and L equal to A times K plus B times L. Then we take the partial derivative with respect to L, right? So since it's with respect to L, we don't care about this term anymore. We just ignore it. It just drops out. And then it ends up just being B, right? Because it's B times 1 times L to the 0. And L to the 0 is equal to 1, so it's just that constant. That ends up, and then this literally is the same as saying marginal product of labor. I mean, like this is by definition. All right, so now let's do the hard one. Let's do the Cobb-Douglas. So we need to find out the marginal product of labor and capital for the Cobb-Douglas function. So remember, this one is Q equals F of K and L equals K to the A, B, or L to the B. And so now it's going to be more difficult when we're taking that partial derivative. So when we take the partial, so let's do the capital first. MPK is equal to partial derivative with respect to K. And so since this is multiplied by L, it's no longer a separate term. So we can't just ignore the L. But we can treat the L as if it's a constant, okay? So essentially you can just take this, treat it like it's 17 or something, right? Put it ahead of it, L to the B, and then do the same kind of A times K to the A minus 1. And that's literally the answer. I mean, we can just rearrange some stuff and do A times K to the A minus 1 times L to the B, just to rearrange stuff. But these are equivalent. They're just as correct. So that's the marginal product of capital when we have substitutability between labor and capital, right? So it makes sense that the labor and the efficiency of the labor are included now in the marginal productivity of capital because there's substitutability. So the amount of capital or the efficiency of capital that I'm using is going to depend on the amount of labor and the efficiency of labor that I'm using. I know this is a little confusing. When I first learned this in grad school, my head was spinning too. So don't get discouraged. Like, honestly, I'm thinking of just canceling chapter 6 because it kind of sucks. And chapter 5 is way important in terms of there's a lot of material packed in chapter 5. So I've already delayed chapter 6's quiz until next week. But I'm thinking because we're behind and because I don't like chapter 6, why don't we just toss it? And you guys aren't ready to do chapter 5 homework anyway, so I should delay that another week. And we might need to meet next Friday. But we gotta power through this stuff. It's a lot of foundational things. And I sent some algebra and some calculus practice out to Priest. I'll send it to everybody as well. So I really recommend, filling your notebook with a lot of math practice, right? Because it seems like a lot of what we're having trouble with is the math part of it and the calculations and the algebra and some of the conceptual stuff, right? So what I told Priest was I was just like, you're trying to understand a new discipline while like translating it from a foreign language because the math is so rusty, and so you're getting tripped up on the algebra stuff, which shouldn't be the kind of conceptual hurdles, right? But they are right now, just because a lot of us are really rusty. We just haven't done a lot of math recently, or we didn't do it as rigorous as this, right? So I'm going to send that out to everybody. I'll delay the chapter 5 quiz. Still do the Learn Smarts though by Sunday. And yeah, we gotta come prepared to class more so that we can do more problems and less lecture. Yeah. So no chapter 6 this week. Chapter 5 I'll delay as well because you guys aren't ready. And then yeah, we might need to meet 3 times next week. We'll figure that out Monday at the end of the class on Monday. Okay. Have a great weekend. I'm going to be grading and stuff this weekend, so you guys will see grades be updated. Just email me if you have any questions.